All right, sum of subarray ranges. So this problem is really similar to a bunch of other problems I've done on this channel, but whatever. We're gonna do it because somebody asked me to do it, and I figured why not. So we are given some array of numbers, and what they want is they just want us to find the maximum and minimum in all the subarrays and add up the differences between the maximum and minimum. So for example, given 1, 2, 3, one possible subarray would be the original array, which is just 1, 2, 3. The maximum number here in 1, 2, 3 would be this 3 here, and the minimum would be 1. So we do 3 minus 1 is 2. And we're going to do this for all the subarrays. So another subarray would be 2, 3. The maximum is 3. The minimum is 2. So 3 minus 2 is 1. And then once we find all the differences, they add them up at the end, and they get 4 here. Okay. The way we're going to do it is we're just going to find all the maximums in all subarrays, add it to a sum, and then find all the minimums and subtract that from our sum. Because it doesn't matter what order we do the addition and subtraction, we're going to get the same result. Like we could subtract all the minimums and add the maximums. And even the way I'm saying it, we're not going to do it in that exact order, but for the way, that's how I want you to think about it for now. But anyway, so let's say we got to go over a couple concepts. So let's say I ask you, how many subarrays is this 5 in, where it is the minimum value? And the way you do it is you need to look for the number to its left, the first number to its left that is smaller than, say, 5 in this case. So what's the first number that's smaller than 5 to its left? That's going to be this 2 here. So we're going to set a boundary here. And you can think of this like the boundary of our possible subarrays. And then what's the smallest number to its right? What's the first number that is smaller to the right? Well, that would be this 4 here. So what we're going to do is we're going to put a boundary to not include the 4. Okay, so these are the possible boundaries of all the subarrays. And now, how many different subarrays can I make out of these boundaries? For example, like this is, so this whole thing is one subarray, right? Well, another subarray would be this. And if we can move the bracket again, this would be another subarray. And now all it comes down to is how many different positions can I put this left bracket in? How many different positions can I put this right bracket in? Well, there's 1, 2, 3 spots on the left, and there is 1, 2 spots on the right. So that's going to be 3 times 2 equals 6 subarrays. And if 5 is in 6 subarrays, that means that it is the minimum value in 6 subarrays. So if we had like a total sum, we would just do sum minus equals that the 6 subarrays times 5, because 5 is in 6 subarrays. So we're just subtracting how many, basically how many times 5 is the minimum in the subarrays. And then let's say we wanted to do, let's try a maximum number. So let's do another example. Let's take this 10 here. No, let's go with a better one. Let's do this 8. Yeah, I'll explain why I didn't want to do the 10 at first. But anyway, let's do the 8. How many subarrays is this 8 in, where 8 is the maximum value? So what you do is you look for the first number to its left that is greater than 8, which is going to be this 10 here. So we're going to put our boundary here, and then so then what's the first number that to its right that is greater than 8? And there is none. So we go all the way to the end of the array. And let's say there was no number that was greater than it to its left, then we would just take it all the way to the beginning of the array. But anyway, so this is where our boundaries are for the left and the right. And now how many spots are there? So there's 1 on the left. So let's just count this. So there's 1 on the left. And now we need to know how many are on the right. So this is going to be 1, 2, 3, 4, 5. Okay, so there's 5 spots on the right. So that means 8 is in 5 subarrays. And then we'll do sum plus equals the number of subarrays, which is 5, times 8, because 8 is in those 5 subarrays where it's the maximum. So, and we'll add this to our sum, right? Because this is the maximum, and we subtract it here because this was the minimum number. And what we're going to do is so this whole process of like finding the number of subarrays and where we find the number of subarrays, we're going to do this for every number and figure out how many subarrays, each value is the minimum and maximum, and we're just going to keep repeating this. So we're going to do it for the 9, the 2, the 10. We're just going to loop the entire array and keep repeating this process. So, and what we're going to do is we're going to do to find these like previous lessers and next lesser elements, or previous greater and next greater elements. We're going to use a monotonic stack. And depending on whether you're looking for your previous lessers or previous graders, you use an increasing or a decreasing stack. So let's just go through an example really quick. I actually have a whole video on monotonic stacks, but that goes into a lot of detail if you really want to like go deep with it. But let's just do a decreasing stack for now. So let's say, so let me just type this really quick. So decreasing stack. So you use a decreasing stack to find your previous graders and your next grader elements. So let me just type that. So this will give us finds previous grader and next grader elements. And let's just go through a quick example of like why that is. Okay, so for a decreasing stack, all we're gonna do, well, the way we start, let's just loop through this array. We're gonna push this 9 into our stack. So pretend I have a stack here. I'm gonna push the 9. Let me put some space here. So I'm pushing the 9 to my stack. It's at the bottom of the stack or top of the stack, whatever. Now I'm going to push this 2. And we can go ahead and push this 2 because we just want this to decrease in this direction. So 9, or basically 2 is smaller than 9. So this is okay. I can keep adding. It's okay to push this onto the stack. But let's say I want to push this 10 here. Well, in order to push the 10, I actually need to pop this 2. So because if let's say I just put the 10 on top, this is no longer decreasing. This is from here to here, this is increasing. So what we're going to do first is we're going to pop the 2, and then we actually have to pop the 9 as well because 10 is greater than 9, and then we just push the 10. And then we can go ahead and push the 8 and the 5. So let's just push the 8, push the 5. And then if we want to push the 7, we got to pop the 5 and then push the 7. Okay, so that's the general like behavior, but like how does this help us, right? Like what the heck is going on? So if actually, let me just leave it like this. So whatever element in this decreasing stack that we end up on top of, that is our previous greater element. So for example, this 8 ended up on top of this 10. So whatever number is directly underneath us is our previous greater element. So if you look at the array, look at this 8, or sorry. So if we look at 8, look at where it is in the array, our previous greater element, our first, which is the first element that is greater to us to our left, is this 10 here. And notice that 10 is underneath the stack, or directly underneath the 8 in the stack. And in the case of 10, where it has nothing underneath it in the stack, that just means that it has no previous greater element. And if you notice, like 10 is actually our greatest element, and notice there's nothing to the left of it where that is greater than it. So that's why there's nothing underneath this 10 here. Okay, and same thing for the 7. Like if you notice, the number directly under 7 is this 8, and 8 is the first number to the left of the 7 that is greater than our 7. Okay, so just remember, the thing underneath us is our previous greater element. And if we were using an increasing stack, it would be our previous lesser element. But anyway, so let's continue. Let me start over because I'm kind of because we need to talk about what happens when we pop elements. And I kind of I showed you the behavior, but I didn't explain what popping something out of the stack actually means in terms of like helping us. So let's just start completely from scratch. Let's say I push the 9 and I push the 2, and that's fine. So 9 is the previous greater element of 2. 9 has no previous greater element because there's nothing to the left of it that's greater. And then I'm going to push this 10. So in order to push the 10, I have to pop the 2 and the 9, right? Well, whatever number I am popping, I am that element's next greater element in a decreasing stack. So this 10 here, if you notice, like 10 is the next greater element of 2. It's also the next greater element of 9 because 10 is the first number that is greater than both these numbers to the right. That's to the right, right? So it's the next greater element. So this 10 here, this 10, because I am popping this 2, that means that 10 is that 2's next greater element. So keep that in mind. Whatever I pop, I am that element's next greater element. So, and then I got to pop the 9, which means 10 is 9's next greater element. and then we could, push the 10 into our stack. Okay, and that pretty much covers the prereqs that you need for this problem. So let's just go ahead and code it. All right, so let's code this out. So really quick, let me just make a little mental note. So an increasing stack is used to find our previous, lesser, and next lesser elements. So finds previous, lesser, and next lesser elements. All right, so now we can start coding. So first, we're going to create our decreasing stack and our increasing stack. So let's do stack of integers, decreasing stack equals new stack. And then we'll do the same thing over here. Increasing stack equals new stack. Okay, and now we're just going to loop through our numbers. So int I equals 0, I is less than nums.length, plus I. And I'm going to write a little helper method. We're just going to push a stack because I don't want to repeat the same code over and over again. And we're going to try to push to our decreasing stack. And our decreasing stack is going to find our previous, graders, and next grader elements. And that'll actually help us find how many subarrays are the elements that we pop out that it is the maximum value in. And then we're gonna sum that up and then add that to our sum. So and I know that's a little rough when I say it out loud, but I think if I just keep coding, you'll see what I'm talking about. So let's declare a little sum variable. So long sum equals 0, and then we're gonna return the sum, right? Okay, and then what we're gonna do here is we're gonna do sum plus equals the result of our push to stack. So we're gonna push into this decreasing stack. It's gonna find the maximum values in the all the elements get popped out. It's going to figure out how many subarrays it is the maximum value in, and then just return the sum of the number of subarrays times that maximum value. Okay, so push a stack, decreasing stack, gotta pass in our nums, gotta pass in I. And I'm gonna do I less than or equal to nums.length. And I know you're thinking, well, aren't we gonna go out of bounds? But there's a little trick to this. But I'll get to it. Just don't get too hung up on this less than or equal thing here. But because I'll explain it later. Okay, so and then what we're gonna do is this would be summing up all of the maximum values, but we also need to subtract the minimum values, right? So we're gonna do the same thing, push to stack, increasing stack, nums, I. Okay, and the only difference between these two, like pushing to a decreasing stack or pushing to an increasing stack, the only difference between pushing to them is the condition of when I add something to, say, a decreasing stack, the thing that all the elements only get popped out at the top of the stack if they are less than the thing I'm about to put in. And then for an increasing stack, it's the opposite, right? Like if I push into an increasing stack, the thing that I'm about to push in needs to be greater than the things at the top of the stack. So then I'll keep popping them out if they don't satisfy basically the opposite condition. So what I'm going to do is I'm going to define a little helper method that just takes in the condition. And yeah, so let me just type it. So we're going to pass in a by function, which is all this is it takes in this will take in the element this will take the element at the top of the stack. So you could think of this as like stack.peak, and B is going to be the thing that we're about to push into the stack. So like nums at index I. Okay, and we're going to return for a decreasing stack. The thing at the top of the stack needs to be, we're going to pop out if it's 3, 2, 1. If it's if it's less than. Okay. So A less than B here. Sorry, I had to think about it a little bit. So for decreasing stack, if the thing at the top is less than the thing we're about to push in, then we're going to pop it out. Okay. And then for an increasing stack, it's the opposite. Oh, this is getting a little long. Let's put this on another line. Okay. So and all it's going to change is the sign, right? So this time, if the thing at the top of the stack is greater than the thing that we're about to push in, then we need to pop out of this increasing stack. Okay. Now let's go ahead and write push to stack. So private long push to stack kicks in the stack of integers, kicks in the stack, and then it's going to be the nums array, and this would be the index in the nums array, and our by function, which is going to be an integer. So these are just the two. This would be like A and B, and then the thing that we're going to return is a boolean. Okay, and we'll just call it compare. Okay, and now we need, okay, so we need another sum variable, long sum equals 0, and then return the sum. So this is just going to sum up the number of subarrays times the max, or times the maximum or minimum value in those subarrays as we pop elements out. Okay, so now in order to push the stack, we gotta check if it's empty. Stack is not empty. And we're gonna check if, so compare.apply. So we're just checking the condition, like basically the property of a decreasing or increasing stack as we're pushing it in. We need to check the condition. So apply stack.peak and nums I. So for example, for a decrease, so let's say we pass in our decreasing stack, we're going to check if this, if the thing at the top of the stack, if it is smaller than the thing that we're about to push in, then we're going to pop it out. So let's just record the index. So let's call this pop I. This is the index we're popping out. Stack.pop. And now we need to know how many positions are there to the left and how many positions are there to the right for that left and right boundary, and then we just multiply it together to get the number of subarrays. So, and then remember, whatever is underneath us, so if this was a decreasing stack, whatever is underneath us in the stack, that is our previous greater element. So whatever was under, so this thing that we popped, whatever was underneath it at the time, which is just going to be stack.peak, this is the index of the next, or the previous greater element. Okay, so let's say if, or let's say, how do I want to do this? Call this int left. No, let's call this previous I. So this would be like previous lesser or previous greater, depending on if this is an increasing or decreasing stack. And we need to check if the stack is empty. If the stack is empty, then it's just -1 because there is nothing underneath it. And if there's nothing underneath it, there is no previous greater or previous lesser element. Okay, and otherwise we just do stack.peak, and that, okay. And now we can go ahead and just calculate the left and the right. So we're gonna do sum plus equals. So let's figure out what's to the left. So to the left is pop I minus previous I. So that's the number of spaces that we could place that left boundary in. And now we need to do the right side. So that's going to be I minus pop I. Let's put that in parentheses. Okay. And put some spaces because I'm picky about spacing. All right. So this would be the number of spaces to the right where we could place that right boundary in. Because, okay, remember, index I is the thing that popped out this index. So that's why I am, so the thing at index I, whatever values at index I, is the next greater element if this was a decreasing stack. Okay. And now we multiply it by nums at pop I. Okay. And we need to cast this to a long because this could get really big. Like if this was like, say this integer is like the maximum integer, we still need to be able to return that sum because they expect us to return a long, and that's like a 64-bit integer basically. So yeah, we just want to cast this to a long so that we don't overflow in case it's too big. And okay, so now I want to talk about, I think this is actually done, but I want to talk about this guy. Why did we do I less than equal? But let me just run it and then I'll explain it, make sure everything's right. Oh, what? What's wrong with this? Why did I output 0? Sum equals 0, sum plus equals... Oh, I didn't actually push the stack. Okay, so push the stack is supposed to push the element into the stack, right? So we took care of popping everything out that breaks our property of the decreasing or increasing stack, but then after we're done popping, we need to actually push the thing into the stack. Okay, stack.push nums I. Oh, no, yeah, nums I. Okay. Oh, no, but so I'm pushing in the index, sorry. I'm not pushing in the actual values, we're doing indexes here. So let's run it. And, oh, okay, so now this is a good time to talk about why did I less than or equal to nums.length. So let's say, let's just do it right here. So let's say that I have an array of 8, 6, and 5. If I push these elements into a stack, so let's say this is a decreasing stack. So you'd push 8, you push 6, and you push 5. And notice that we were able to push all the elements into the stack, into a decreasing stack, and nothing gets popped out, right? So we end up having, once we're done looping through this array and pushing everything in the stack, our stack has these like elements still inside of it. So what we need to do is we need to call push to stack one more time to pop these elements out to figure out how many subarrays those numbers were the maximum value in. And what this means, because what it means for them to not get popped out, they just have no next greater element. So if you look at our array here, 8 has no next greater element. There's no element to the right that is greater than 8. And there's no element to the right of 6 that is greater than it. And there's no element that is greater than 5 to the right, right? So what that means is that the boundary for the right side is here. So that's why we do I all the way to the end of the array. So I is just going to equal the length of the array. And notice that that's essentially what this represents here. And so if we were doing the 8, this would be like the previous greater position would just be here, right? And if we were doing the 6, the previous greater position would just be here, because 8 is underneath 6 in our stack. So that means 8 is the previous greater of 6, and you could just tell by looking at the array, right? At the end of the day, we're just doing I less than or equal to nums length so that we can pop out these last elements in the stack. And let's do a little check here. So, and I is equal to nums.length or the condition was broken. So if I is equal to the nums.length, we're just going to short circuit here. We're never going to check this condition. And so if I is equal to the end of the array, just keep popping and calculate the left and the right positions. So you calculate the left and the right positions and multiply it by the actual value, and then that gives us the sum that we're looking for. Okay, so all this did was we found all the elements that we popped out. We find how many subarrays those maximum the elements that we popped out, how many subarrays were those popped out elements, the maximum value in. We add that to our sum for the decreasing stack, right? And then for the increasing stack, that helps us find the minimum values. So all the elements that we popped out, how many subarrays are those values the minimum in? And then we sum that up, and then we subtract that from our total sum here. So that's why we did subtraction here. And then, we just return our sum. So this should work. Let's just run it. And it doesn't work. What did I do wrong? Casted this to a long. Sum pushes stack. What's going on here? This looks perfect to me. Give me a second.
A few moments later.
Oh, okay. So I'm pushing in the indexes into the stack, but right here, the stack.peak, I needed to do, because this is peaking at the index in the nums array, I need to do nums of stack.peak here. Okay, that was a silly little mistake. I think that's it though. Let's see, run it, submit. Okay, cool. And so that's pretty much how you do the problem. So the time complexity is just going to be O of n, because we're only going to push all the elements into the stack one time, and we're going to pop them out one time. So that just ends up being O of n. And the space would just be O of n too, because of the stacks. Okay. So yeah, if you liked the video, you can give it a thumbs up. You can subscribe if you want. Cool, bye.